The present problem is of gate 2008, and this problem is of common data type with 3 linked problems of 2 marks each. And this problem is in the area of digital communication. We'll read out the problem here. A speech signal band limited to 4 kHz and peak voltage varying between +5 and -5 volt is sampled at the Nyquist rate. Each sample is quantized and represented by 8 bits. First problem is, if the bits 0 and 1 are transmitted using bipolar pulses, the minimum bandwidth required for distortion-free transmission is. There are 4 options: 64 kHz, 32 kHz, 8 kHz or 4 kHz. Now the second problem is, assuming the signal to be uniformly distributed between peak to peak value, the signal to noise ratio at the quantizer output is 16 dB, 32 dB, 48 dB, 64 dB. The third problem is it's on the number of quantization levels required to reduce the quantization noise by a factor of 4 would be 1024, 512, 256, 64. So these have been the 3 problems, and we'll see the solution to these problems. Now we can see the first part, that is this is, you notice here it is given that speech signal is band limited to 4 kHz, and the corresponding Nyquist sampling rate is the minimum sampling rate for recovery of the signal, set twice the maximum frequency. So 2 into 4 kHz, that is 8 kHz. Now bit rate is given as n, the number of bits per sample to sampling frequency. So this is 8 into 8 kHz, 64 kbps. This is the bit rate, and minimum transmission bandwidth needed is RV by 2, that is bit rate divided by 2, that is 32 kHz. What we observe here is that the 32 kHz option is the right option, but what we observe here is that when the signal is analog, a 4 kHz band limited signal needs a bandwidth of 4 kHz. When this signal is sampled and made digital, the minimum bandwidth required is now 32 kHz. So it is 8 times. So when you digitize the signal, the required bandwidth increases. That's what it is indicating here. Now the second part is signal to noise ratio. The problem is that signal to be uniformly distributed between peak to peak value. The signal to noise ratio at the quantizer output is that we have to find out. Then signal to noise ratio, our signal to quantization noise ratio in dBs, the relation is 1.76 plus 6n in dBs. Approximately this could be written as 6n dBs, where n is the number of bits per sample. Now this 6 n is 8 bits, so 48 dB. So it is signal to noise quantization level is 48 dB. Now we see the third part here. What we have to find is, we have to find the number of quantization levels to reduce the quantization noise by a factor of 4. So we know quantization noise is given by delta square by 12. This is step size. This could be further expanded, this would be VPP, peak to peak voltage, divided by L whole square, this is delta whole square divided by 12, and this would be VPP whole square divided by 12 L squared. So we observed here that VPP is a fixed because we apply a fixed input. So NQ, quantitation noise, is proportional to 1 over L square. That means if you have more number of quantization levels, the noise would be less. So to reduce the quantization noise by a factor of 4, the quantization level should be twice L, because 1 over L square relation. So L equals to, we know that levels equal to 2 to n, 2 to 8, 256 levels are present, and you need twice L. That means these levels have to be enhanced from 256 to 512. Okay, so this is option B, and this is the right choice. Option B is the right choice. So these have been 3 problems, and they are quite simple if you understand the parts given in this problem. Thank you.